Welcome back to another Explainer. Today, we're diving into the exact under-the-hood technology that allows the AI tools we use every single day to read entire books or massive code bases in a matter of seconds. I mean, if you've ever dropped a gigantic PDF into a chatbot and watched it instantly summarize the whole shebang, you've benefited from a pretty monumental engineering breakthrough. So, we're going to dissect the systems architecture that actually makes this possible. Context parallelism.
We have rapidly, and I mean rapidly, entered an era where language models are expected to process a massive 1 million tokens in a single prompt. To put that into perspective, that's roughly equivalent to feeding an AI the entire Harry Potter series, plus The Lord of the Rings, all at the exact same time. Models like Gemini 1.5 Pro already boast a 1 million token context window, and systems currently in development like Llama 4, well, they're targeting up to 10 million tokens. The demand for processing vast amounts of spatial, temporal, and text data is just absolutely exploding right now.
So you might be wondering, how in the world do you actually fit 1 million tokens into a GPU that only holds a tiny fraction of that? Let's dive into this and uncover how systems engineers are solving the massive hardware challenges behind this memory monster. A single state-of-the-art GPU, like an NVIDIA H100, is incredibly powerful for sure, but it has strict memory limits, typically right around 80 gigabytes. When you try to cram millions of tokens into just one GPU, the math literally breaks the machine. You run out of memory before the model even finishes reading the very first chapter. Because we're exploring some pretty complex distributed systems architecture today, here's a quick roadmap for our explainer. We'll start with the memory monster, move on to context parallelism and ring attention, talk about the workload imbalance trap, and wrap up with advanced load balancing. All right, let's kick things off with Section 1, the memory monster, the quadratic bottleneck. Let's start by understanding why asking an AI to read a really long document is just so mathematically punishing. You see, while model parameters grow linearly, the attention mechanism scales quadratically, and that is absolutely crucial to understand. In a standard transformer model, every single token has to pay attention to every other token in the sequence to build context. Mathematically, if you double the sequence length, the memory required for that attention matrix doesn't double, it quadruples. For instance, at just a 128,000 token sequence length, which is well short of 1 million, the vanilla attention implementation requires roughly 32 gigabytes of memory for just a single attention head. Multiply that by the 128 attention heads found in a model like Llama 3 45B, and well, it's mathematically impossible to fit that on any single GPU on Earth. Moving right along to Section 2, enter context parallelism, sharding the sequence.
To solve this impossible math problem, the industry had to evolve way past traditional parallelism strategies. Context parallelism shaves down communication costs compared to tensor parallelism, making it the ultimate answer for these massive sequences. Historically, engineers used tensor parallelism to slice the model's weights across multiple GPUs. But context parallelism does something different. It leaves the model completely intact, but slices the input sequence itself into chunks, distributing those chunks across the GPUs. And it gets better. Modern architectures use grouped query attention. This is a really clever trick that groups the data so there are far fewer key and value heads than query heads. Because context parallelism is primarily communicating these much smaller key and value tensors across the network, the communication traffic drops by an entire order of magnitude. It is just an incredibly elegant mathematical trick to save bandwidth.
Which brings us to Section 3, how ring attention works, passing the notes.
To actually compute all this, context parallelism relies on a mechanism where the sequence itself is sharded and passed around. Imagine a group of friends trying to read a massive book by each taking a chapter and then passing their notes in a circle until everyone understands the entire plot. That's essentially what these GPUs are doing. Under the hood, this happens using two main strategies, all-to-all ring rotation or all-gather. Now, in a perfect theoretical world, all-to-all sounds great. GPUs pass key and value shards in a circle, computing attention step by step. But in practice, achieving perfect overlap between computing and passing data is nearly impossible. It leads to idle time where GPUs are just sitting there waiting. That's exactly why all-gather is often the default. It simply gathers all the necessary pieces at once. Yeah, it creates one larger pause for communication, but surprisingly, extensive benchmarks show it frequently outperforms the constant smaller delays you get with ring rotation.
The massive leap in context size that ring attention enables across different model sizes is honestly staggering. Compared to older baseline models, we are jumping from a few thousand tokens to millions of tokens, and doing it without having to approximate or lose any data fidelity whatsoever. This is the exact architecture that suddenly made it possible to upload a 500-page financial report and just ask for a detailed analysis on the fly.
But as always, there's a catch. Let's look at Section 4, the workload imbalance trap, real-world data. Just when it seems we've totally solved the memory issue, we hit an unexpected complication with real-world data. Real-world documents aren't perfectly uniform. You don't train an AI purely on perfectly sized 100,000-word books. You're training it on a super messy mix of Wikipedia articles, short little tweets, medium-length code snippets, and massive transcripts. To be efficient, systems use something called input packing, basically concatenating multiple short documents into one long sequence so they don't waste any space. But to prevent the AI from getting confused, they use document masking. This just ensures a token from a Wikipedia article doesn't accidentally pay attention to a token from some random tweet packed right next to it. So here is the crucial point. Chopping up these unevenly packed documents across GPUs creates massive workload imbalances. If a naive context parallelism system just takes a packed sequence and chops it exactly in half, well, it's kind of like assigning one student to read a dense encyclopedia and another to read a comic book, but giving them the exact same time limit. The GPU with the long document is completely overwhelmed, while the other is just sitting there idle. And worse, because attention computation is quadratic, that GPU with the long document has to do exponentially more math. Plus, the GPUs are passing around full key and value tensors for the entire sequence, even though that document mask we talked about means they only actually need the data for their specific document. It ends up being a massive waste of both compute power and network bandwidth.
Which leads us to our final stop, Section 5, Advanced Load Balancing, Flash CP and WLB LLM.
To rescue our GPU efficiency, frameworks like Flash CP and WLB LLM step in. They solve this by dynamically keeping short documents whole, smartly shifting workloads around, and delaying extremely long outlier documents. Instead of just blindly chopping the sequence into equal lengths, these advanced systems analyze the document lengths before they even start sharding. They actually try to fit whole documents onto individual GPUs to eliminate cross-GPU communication entirely. If a document is just too long, they adaptively shard only that specific document to balance out the math. And what about those wildly long outlier documents that would normally bottleneck the whole system? Actually, they just actively delay their execution, combining them later in a way that doesn't hold up the rest of the microbatches.
By eliminating all that redundant communication and balancing the math, these optimizations deliver up to 1.3 times the speedup over baseline context parallelism architectures. Now, I know what you're thinking. A 30% speedup might not sound like a world-shattering number at first glance, but you have to scale it up. When a company is training a frontier model on 16,000 GPUs for 3 straight months, a 1.3x speedup translates to saving literally weeks of compute time. We're talking tens of millions of dollars saved in electricity and hardware rental costs. It is an absolutely massive, game-changing win for systems engineers. As these systems engineering breakthroughs completely remove our hardware limits, it really leaves us with a huge question. What happens to AI capabilities when the context window becomes, well, everything ever written? We've gone from struggling with a few paragraphs to comfortably analyzing millions of tokens, and it's all thanks to the clever sharding and balancing of context parallelism. If the hardware can now support practically infinite context, the only limit left is our imagination on how to actually use it.